Hello and welcome. In the last lecture, we had seen how we can increase the bandwidth of the antenna. So, we had actually noticed that the bandwidth of the antenna can be increased by increasing the substrate thickness or by reducing the dielectric constant. Then we also looked at multiple resonator techniques, where we had put one patch on the one side of the rectangular patch antenna, and this was a parasitic antenna, not fed, only one patch was fed, and we actually noticed that the bandwidth of the antenna can be increased. We also saw the parametric effect. What is the effect of the gap? That means, if the gap is increased, coupling is reduced and thereby loop size is reduced. We also saw what is the effect of the feed point. That means, if we shift the feed point towards the edge, the whole impedance shift towards the higher impedance value. We also saw what is the effect of the length of the parasitic patch. So, as the parasitic patch length increases, its resonance frequency will decrease. So, the loop will shift in the anti-clockwise direction. Of course, in the last lecture I had mentioned, if the patch dimension is decreased from 3 centimeter to 2.8 centimeter, its resonance frequency increase, hence the loop moved in the clockwise direction. So, you should understand that what happens if the length changes. So, then what we had seen, instead of 2 gap coupled, we had put 3 gap coupled antenna, because by putting 3 gap coupled antenna, the pattern variation was relatively less over the bandwidth and the radiation pattern was in the broadside direction. Then we talked about non-radiating edges. So, where we had put the patches along the non-radiating edges, and again we saw that the bandwidth can be improved. So, now today we will see that how we can put patches on all the 4 sides to get the better bandwidth compared to the earlier 2 things. So, let us see the configurations now. So, we had actually looked at radiating edges coupled, where we had put the antenna along the radiating edges, and what we had also noticed that the radiation pattern varies in E plane, but there is no change in the radiation pattern in the H plane. Then we had put parasitic patches along the non-radiating edges, and again in this case we had mentioned that this case now the pattern variation in E plane will be not there, but pattern variation in H plane will be there, because parasitic patches are placed along the non-radiating edges. So, here we have now 4 edges coupled rectangular microstrip antenna, where antennas have been put on both the sides here. So, here now again we can choose patch length here, let us say L1 L1, so that this will be symmetrical. We can take these 2 patches as L2 L2. So, what that would really result into, that at L1 these patches will be resonant and it will be symmetrical. At a slightly higher frequency, then these patches will be resonant, and since it is still symmetrical, pattern variation will not be there over the bandwidth. And by choosing the 2 lengths different L1 and L2, we will see that 2 different loops can be obtained in the Smith chart plot. So, let us take one of the example now. So, we will take a similar example as before, which is the substrate parameters are same, epsilon r 2.5. We have taken a thicker substrate as an example, so that we can get a larger bandwidth. But compared to the previous case, width has been reduced. The reason why we reduced the width, actually we were not able to get the impedance matching by using a simple coaxial feed point. So, that is why we reduced the width here, and now L1, which is along the radiating edges, is 27.5 mm and the gap is 2.5 mm. So, I had mentioned that along the radiating edges gap can be little larger, whereas along the non-radiating edges we have kept this dimension smaller than this here, so that it will have a slightly higher frequency. Along the radiating edges gap has to be small, and then that is reduced to 0.5 mm. Just to mention again, earlier we were talking in centimeter, here we have mentioned the dimension in millimeter. Now, the feed point is 14 mm, you can see that L is 30. So, half of L will be 15 mm. So, this is almost at the edge of the patch. Okay. So, now we can see there are 2 loops in the Smith chart. So, let us see, this is the loop response over here. So, this loop is corresponding to length L1, and then that is appearing at the lower frequency, and then while it is completing, the another loop is formed because of this length here, and hence we see two different loops here. And one can see that both the loops are within VSWR equal to 2 circle, and that gives us a larger bandwidth. So, this is the VSWR plot versus frequency. So, if we draw a line from here, we can see what will be the VSWR less than 2 bandwidth, which we can see here that the bandwidth is about 569 megahertz, that is close to 18%, and this is much larger bandwidth. In fact, in case of radiating edges, we had got a bandwidth of roughly around 12%, and again for non-radiating edges we got around 12%. Now, we are getting about 18% bandwidth. Okay. Now, of course, here it requires a lot of optimization techniques to bring both the loops inside the VSWR equal to 2 circle. So, these lengths can be optimized. So, just to give little bit of a concept here. So, if this length is taken, let us say larger than this, if it is large, what will happen? Its resonance frequency will reduce. So, the loop will be formed somewhere here, and the gap over here controls the size of the loop here. So, one can actually reduce or increase the gap. Similarly, over here now, this loop dimension, if we take let us say slightly larger, then what will happen? If this is larger, this loop instead of coming over here, it will actually form right over here also. Okay. But if we take less dimension than this, then the loop will go outside the VSWR equal to 2 circle. So, it is really important to optimize the gap. The width of the patch also plays an important role, because by reducing the width, we can actually try to optimize the feed point location. So, no external impedance matching is required then. So, let us see the radiation pattern. So, here we have shown the radiation pattern at 3 different frequencies. One is near the center, and this is on the lower band edge, and this is towards the higher band edge. So, at the lowest frequency, it is the central patch which is resonant. So, the radiation pattern is in the broadside direction. Now, at in between frequency, now just to recall, this is the patch dimension along the radiating edges. So, this will be the intermediate frequency, and this will be the highest frequency. So, you can see that H plane pattern is not changed much, but E plane pattern has changed, but it is still in the broadside direction. Okay, because the patches along the radiating edges are more dominant over here. At the higher frequency, patches along the non-radiating edges are more dominant. Now, one can see that E plane pattern has not much changed here, you can see somewhat similar, but now H plane pattern has changed. Okay. So, one can see that this is the H plane pattern. Now, you can actually notice one additional thing, that for the H plane pattern, this one has a much higher value compared to the H plane pattern. Now, see, this can be explained in a simple way. Along the E plane, we have a pattern which is relatively has a higher value, but along the H plane, the element pattern is relatively going towards 0. So, it is this value here which is getting multiplied to the array of the elements, and that is what is bringing it back to close to 0 here. Otherwise, it would have also followed the similar trend of going out, but since the pattern of element itself is going towards 0, so 0 getting multiplied with this array factor point here, it tries to bring to the 0 here. So, hence H plane pattern looks relatively better compared to the E plane pattern. So, now because of these multiple patches, gain also is slightly more than the single patch. Okay. So, that means by using 4 gap coupled antennas, what we can achieve? We have achieved a much larger bandwidth, and we have also achieved higher gain. I also want to mention here, if we had taken this length L1, 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 all of these are taken as L1, then what would have happened? There would have been only one loop in the Smith chart plot, but then all the patches will be resonating simultaneously, So, it actually gives rise to a higher gain. So, there is a trade off between the gain bandwidth. You know that in general gain bandwidth product is relatively constant in case of an amplifier. Well, it is not always applicable 100% to antennas, but somewhat applicable here. So, over here just to repeat, if this is L1, L1 and if this is L2, L2, we will get a broader bandwidth, but slightly less gain. But if we take this L1, 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 then bandwidth will be slightly less, but gain will be slightly more. So, instead of using these gap coupled, one can go to the next configuration, and which is known as directly coupled RMSA. So, here just to show, so this is radiating edge coupled, this is non-radiating edge coupled, and this is all 4 edges coupled. Let us just look one by one now. Now, for the radiating edge coupled, you can see that a line strip is connected over here. So, here the coupling is controlled, of course, the gap S. What we have tried to do here, we have taken this gap S now greater than 2H, where H is the substrate thickness, because see, recall absolute maximum fringing field can be extended to about H, and this can be extended to H. So, if we take greater than 2H, gap coupling will not be there. So, direct coupled where the gap is generally taken as larger. However, we can also use the hybrid coupling where S will be smaller than 2H, then there will be gap coupling also, and there will be direct coupling also. Okay. And here the coupling depends upon the width of the this connecting strip over here, and by optimizing now this gap and this width of the thing, one can actually optimize the coupling between the patches, and hence one can optimize the bandwidth in a very similar way as that in the case of the gap couple. Now, in non-radiating edge, there is one additional parameter which controls the coupling between the patches. So, over here it was generally the width of the strip here which was controlling the coupling, but over here the location of the strip also controls the coupling. The reason for that is over here the radiation is uniform along the width, but along this length here the field variation is sinusoidal. That means this is plus here, 0 here, minus here. So, it varies sinusoidally plus 0 and going to minus here. So, if we connect right at the center here, okay, and center here, actually speaking there will be absolutely no coupling to this particular patch because the field is 0 here. So, that means now if we move this strip here along this side, since the field is increasing, so as we move this connecting strip along this direction, coupling will increase. So, here coupling to this patch or this patch here will increase if we shift the coupling strip location along this edge, and also what will be the width of the strip over here. So, now we have many more parameters which can be optimized to get a broader bandwidth. Now, over here now the same concept is extended. So, the edges are coupled along this here and edges are coupled along this one here. Now, I want to mention here that this concept is different than the array. In fact, I just want to mention, so we had written a paper on directly coupled RMSA almost more than 30 years back in 1984 or so, and I also want to mention that what we have covered about directly coupled and as well as gap coupled rectangular microstrip antenna, all these were part of my PhD thesis which I started working in 1979 and submitted the PhD thesis in 1982. And I just want to mention that see microstrip antenna practical part came only in about 1974 when Munson had proposed microstrip antenna. From 74 to 79 hardly 5 years had passed and very little literature was available. So, in the beginning it was really a lot of struggle. So, we really had to do lot of optimization, we had to do lot of programming also, and those days I had written program in Fortran and I did PhD from IIT Kanpur, So when I started working on this, so we did not have these fancy terminals and we could work on that. Those days we had to punch each and every line on a separate card, and we will have a stack of these cards. We will go to the computer center, give it over there, and then if there is even a small mistake, it will just give the errors. Then you get that printout of error, you go through that, you correct the thing, then you again submit it, and then even if the order changes, again you will get all the error messages. So it used to take lot of time those days when we were working on these things. And of course, while I was doing PhD, then these terminals came, and then we started having, enjoying the luxury of using terminal, but the computers were really slow, and during the day it was really a difficult thing. Computers were so slow, the terminals were fully crowded, students were working. So just to tell you, I always used to be a morning person. I used to get up early, 4:30 a.m., would study for 2 hours, then do my classwork and other thing. But then during that PhD program, then I actually became a night person, because I realized that computer center was relatively free, because lesser students were going during the night time. I'm talking about 1980 or so. So then I developed the habit of going after dinner and then work almost whole night, and then come back to the hostel, take breakfast, and then start the day. So from those days, and now we have the luxury of all the computers, desktop right on our rooms here, and we can actually use the power of the computer. But nevertheless, when we submitted this paper here, so the reviewers had asked us one question: so how this particular thing is different than arrays of antennas? Because in an array, what we do, we also feed all the elements. So it also looks like it is not really a parasitic element. We are feeding this one here and this one. So I actually gave the explanation that this is different than the array. See, in the case of array, what we do, we have all the patches of equal dimension, and then all the patches are fed with, let's say if we want a broadside radiation, then all the patches are fed with equal amplitude and equal phase, and that would mean that the phase difference between this and this should be, if I connect here, it should be 180 degree phase shift to be given, or if I feed here and here, then this should be 360 degree phase difference, so that will amount to 0 degree phase difference. So over here we have optimized for the bandwidth, not for the gain. In the case of array, we do not optimize for the bandwidth, but we optimize for the gain here. So it is not same as array antenna. So here we have chosen the patch dimensions slightly different, so that we can get a broader bandwidth. So these details now you can also see in my book, Broadband Microstrip Antenna. In fact, that book is freely available now through the internet. So you can download also, or you can purchase it. It is available from the Artec house. So it's your choice. Let's just move to now the next configuration, which is gap coupled circular microstrip antenna. So here we have a circular patch here, and the two patches are put on the left and right side, just like a radiating edge here. Now here I would just want to mention here that during my PhD thing, I had worked on mainly on the rectangular microstrip antenna, and we had proposed some broadband configurations using triangular microstrip antenna or circular microstrip antenna. Fortunately for us, nobody really had worked on this configuration, and I revived this configuration almost, you can say, 15 years later than my PhD. So it was much later we started working on this here. And now I just want to tell you, so those days I did not have these fancy commercial software like i3D or CST, Microwave Studio, ADS, HFSS, and so on. So we thought, okay, why not we do one experiment? So we put a patch over here and we put the patch on this side. And in fact, when we did the first experiment, we actually made this patch, let's say radius A1, this we made as A2, this we made as A3, so that the two patches are resonating at different frequency to obtain larger bandwidth. However, when we made the first experiment and we fed over here, actually speaking we did not get any loop. Okay. We only got the response of this particular thing, these two actually did not do any contribution because they were not getting coupled properly. So, then we did another experiment where we reduced the gap significantly, and now we could see a very small kink instead of a loop in the Smith chart plot. So, then we started thinking what is happening. So, at that time I used the concept of the direct coupling. So, what we did, we put a copper strip and we put those copper strip along the gap. So, we put copper strip one by one. So, we put one copper strip on the right side, then we put another copper strip on the left hand side, and we could see that the coupling is increasing. So, by using that concept, then we could increase the coupling on this side or we could increase the coupling here, and then we started thinking why this is not happening. So, just to tell you what is really happening here, compared to the rectangular patch, in case of a rectangular patch, this is the entire width is there, and for the parasitic patch also there is the entire width. So, coupling is there along the full width of the rectangular patch, but over here because of this curved surface here, coupling is mainly due to these closer points here. The moment we see over here, the coupling almost is reduced to negligible value. So, hence gap has to be reduced very significantly. I also want to mention that gap is also related with the thickness of the substrate. It is always S by H which is important and not S alone. So, what we did later on, then we optimized this particular thing, we took a little thicker substrate, and of course, by that time we procured the i3D software, we did the simulation using i3D, and then what we did, we kept this patch and this patch same radius, so that we get a similar radiation pattern which is in the broadside direction and pattern variation will be less. So, that is how we did the optimization for this case here. The results are very similar to the radiating edge gap coupled, we could get a broader bandwidth as well as higher gain. Now, for the non radiating edges, one has to do little more thinking. One should not just put over here the patch along the non radiating edge, because see field is 0 here which goes to plus, right. So, if you put here the another patch in this side right here and here, coupling to that patch will be close to 0. So, we found an alternate way by knowing the field distribution. So, we know that this is let us say 0, if I say this is plus, it is double plus, and then this will be say 0 minus double minus. So, double plus means higher amplitude, then lesser amplitude, and then 0 amplitude. So, here now the patches are put along 45° from this axis here, and these are placed symmetrical, and by placing these symmetrical, and what we also have done, we took all the 4 patches of equal radius, and then this is a slightly different radius here. So, all these patches then resonate simultaneously. Now, then we also came out with a slightly different configuration over here. You can actually think about this configuration as kind of combination of this, but you can actually think that this is the radiating edge, that was the term which we had used for the rectangular patch. This is of course not edge here. So, we can say that it is put along the E plane instead of calling it a radiating edge couple. Now, what we have done here, we have put 2 patches over here, and so the coupling is through this side, and they are also getting coupled with each other. So, these results we have optimized, these results are very similar to that of the rectangular patch, and for more details you can see the broadband microstrip antenna book. Okay. Then we actually came out with another idea when we discussed about a circular microstrip antenna as well as semicircular microstrip antenna. So, what we had seen that the resonance frequency of circular microstrip antenna is same as that of a resonance frequency of semicircular microstrip antenna. Okay. So, here what we have done here, this is of the same radius as this here. So, now you might wonder if this radius is same as this, then their resonance frequency will be same. Actually not really, this patch is being fed. So, it is fed with the coaxial probe. a coaxial probe will have some inductance. So, because of that inductance, resonance frequency of the fed patch is slightly less than the resonance frequency of the non-fed patch. So, one can actually see that these two are getting coupled, and one can see that there is a loop in the Smith chart, and this one here gives a bandwidth of about 143 megahertz, which is about twice the bandwidth of circular microstrip antenna on same substrate. However, I want to mention here that in this particular case, gain is not uniform over the bandwidth. So, yes, we are getting more bandwidth by using two gap coupled semicircular microstrip antenna, but gain varies over the bandwidths. If that is acceptable, then only one can use this particular configuration. So, similar to that, we have also repeated something like which I mentioned about equilateral triangle in the last lecture. So, in the equilateral triangle and the 30, 60, 90 degree triangle also, they both have a same resonance frequency. So, they can be get coupled also, and one can get a broader resonance frequency. Now, similar to rectangle or circle, one can also put triangular patches which are gap coupled, and you can still get a larger bandwidth or gain. So, their effects are very similar. So, now let me show another configuration. This configuration was reported a long time back, where what was done is that this is the rectangular patch here, and over here the resonant length is 12.45, width is very large, which is you can say close to 22 here. Now, what has been done here, a slot has been cut over here. Now, by cutting this slot here, one additional resonance has been obtained. So, the resonance frequency of this slot should be close to the resonance frequency of the patch here, and then one can get a much broader bandwidth. In fact, this configuration became very popular at one time. The reason for that is that this particular configuration achieved wider bandwidth without increasing the volume. So, if you recall, the bandwidth can be increased by increasing the substrate thickness. So, that means volume is increased, or bandwidth can be increased by reducing the epsilon r, that will increase the aperture area, that means again volume is increased. Or we looked at the gap coupled configuration or directly coupled configuration, again the overall patch dimensions are increasing, that means volume is increasing. So, this became a very famous configuration where volume was not increased, exactly the same volume was there, and in that volume itself the slot was cut over here to increase the bandwidth. So, we also got carried away, a lot of other things have been done here. So, instead of using a U slot, we also use V slot. Instead of using a one U slot, two U slots were used to get even better bandwidth, and lot of slots were cut in between. There were toothbrush slot and many other things had been reported. But I want to mention here again, the major problem with this configuration is that gain is not uniform over the bandwidth. So, yes, within the same volume one can get a larger bandwidth. In fact, the same thing was also, you can say here, the volume is same here as that of a circular patch, bandwidth is increased, but gain is not uniform over the bandwidth. So, please remember that when you are designing the antenna, it is not VSWR bandwidth is important, but it is also the gain bandwidth is important. Pattern variation over the bandwidth is also important. So, today we have discussed about how to increase the bandwidth by using gap coupled configuration along radiating edges, along non radiating edges, along 4 edges. We also looked at the directly coupled configuration, but in all these cases we saw that the dimensions were increasing in horizontal, or you can say in planar dimension. In the next lecture, we will now see how the bandwidth can be improved by increasing the thickness, overall thickness of the antenna, where we will have a one bottom patch, we will put another patch on the top, and these two patches will be resonate at a similar frequency to get wider bandwidth. And after that, we will also see how to use combination of this. So, where we will go in the planar dimension, either in this plane or that plane, or we will go in the vertical direction. So, by using combination of that, we can get even larger bandwidth. So, we will see lot of more broadband configurations in time to come. Thank you, bye, and we will see you next time.